All right, so we made some slides, but like Alyssa has said, feel free to interrupt or slow us down or anything as we go. So we're going to be talking about introductory courses specifically, and Ellis has let me go first, so it's actually biology and then some chemistry. But we are going to be thinking about the elements of a cure and how they might mesh with your course objectives or your program objectives. And then also some ways to kind of spice up a cure once you've started it. Things that we have found enhance teaching in a cure. So here's our general plan. I'm going to start just with a explanation of what I mean when I'm thinking about cure elements, and then I have, excuse me, I can show you our outcomes and how they do or don't match up with the elements of the cure. And then I'm going to give a little bit of advice in some sense about starting small and how to build into a bigger cure or how to build your students up so they're ready. And then I'm going to talk a little bit about collaborations. And then at that point, we're going to kind of switch. And Ellis is going to emphasize some networks and organizations that can help you develop a cure. And again, talk about cure elements and how they match with chemistry outcomes and give some specific examples from his own teaching. So when we say elements of a cure, this is a fairly comprehensive list. We have noticed that there are different lists given by different people. But when we're thinking about a cure, we want to be working on something that has relevance to the scientific community and that students can understand why you would be studying that. And you give them a chance to learn the scientific background in some depth and develop a hypothesis. And one of the things that Ellis and I have really done is lean hard into that part of the cure, making students not just spend 2 seconds coming up with a hypothesis, but actually thinking about what evidence do we have, what kinds of things would we want to know before we even get to the point of making a hypothesis. And then some sort of proposal. It can be bigger or smaller. I've actually gone to a format where students record themselves with some slides talking about their proposal, mostly as a defense against AI, but that's what I've done with the proposal. And then experiments, and usually at that point is a really good time to make sure that you have teamwork and collaboration incorporated into the cure and emphasizing reproducibility, and then leading students to analyze their data, make evidence-based conclusions, and then again, some sort of presentation of those results. When I thought about my learning outcomes, I kind of have 2 things to guide me in the class that I am going to be thinking about today with the cure and intro bio. We have Minnesota State biology transfer competencies. These have been agreed to by a very large committee of people from all of our community colleges and the state universities. I was pleased to see that this list pretty much is the same as the list that I just put up there. Most of the elements of the cure are competencies that I should be developing in students as they go through our program, with a little bit of strange emphasis on microscopy. But other than that, this list is kind of very, very well fit to a cure. So I feel like I don't have any problem teaching with cures because this is what will give my students the competencies that we're hoping to get them in the program. On the other hand, when I look at my course objectives, which are it's overwhelming. I will tell you the course objectives are quite this is only 1/3 of them, but these are the ones that are related to the lab. They're extremely specific. And so I don't expect you to read them, but what I will say is that there are some things in here that I cannot do in the current cure that I am doing because my cure cannot cover all the things. But what I have noticed is that when you are planning to add a cure to your course, it is quite helpful to start small And one of the ways you can start small is by not necessarily doing the cure work every single day in your lab. And that's how I decided to start. When I began doing cures with Ellis, I said, well, I have all these learning objectives. I just can't do your cure for the whole semester. I have to teach DNA technology. I have to teach microscopy, and those don't fit in this particular project. And Ellis was supportive of that, and that was a good thing because then I just went ahead and fit in what I could. And then I found ways creatively to expand my cure until now I'm actually teaching what I would call a full semester cure. But I still feel that I am meeting my learning objectives by being a little bit creative about my schedule. I would advise you that if you are just getting started with a cure or just getting started at an intro level with a cure, that you may want to start what I would call small. Okay. And when I'm saying start small, think about, is there one course that you can start with? Is there maybe a course that only has one section, or could you just pull one section and do that a little bit differently until you feel comfortable? It probably helps if you are not needing to coordinate your instruction with a whole bunch of other people, unless they are your work spouse and are on board with you. So for me, that was describing my majors bio 1 class. That was a standalone one section course that I could teach every semester if I wanted to by myself. So that's where I started. And I did what I was saying before, just a short, like about half of my lab was devoted to the cure work. So about 6 of the 12 to 15 meetings in a semester were cure related. I did put strategic gaps into the schedule. That at the beginning, I was getting some materials from other people who were collaborating with me. And so I needed time to figure out what those materials were. And then they kindly sent me stuff in the mail. So I had built in a few weeks, like around breaks or other things that we were doing to make that work. Eventually now, I would say that I am doing what I call a complete cure or a full semester cure, because there are several days when there is something that we need to do for the cure that takes some time and concentration, but we cannot necessarily keep the students focused on it for the whole lab session. So, for example, I do need to teach microscopy. I do that on the same day that we are doing our lit review. So we do lit review for a while. We look at microscopes for a while. I do DNA work. We do it on the same day that we're working on the posters. So again, it kind of breaks up the session for the students. So it's not that I'm not teaching those skills, it's just being a little bit strategic about it. And again, this is helped because I am in complete control of my schedule because I'm the only one teaching that course. I also then, I would say, expanded further. I started doing a related cure in a different course, kind of in the same way. I started with, some of the course time being devoted to it, and then that expanded to more. And now the students in the 2 courses are collaborating with each other. And so here's a example of what I would call a mini cure. In my course, I start with the same kind of general lab skills that you probably are, like teaching students how to use pipettes and measure and how to use a spec or make standard curves and graphs and things like that. And then I introduced them to our topic. I did have an assignment related. I pretty much have a small assignment every week. That's something I'm going to talk about in a minute. But at the beginning of the semester, they had 2 sessions to kind of get into the topic and develop a hypothesis. And in the mini version of the cure, the hypothesis was only written up in like a short paragraph. They did not make a full proposal. Then we had a break. Like I said, that was time to get things delivered in the mail and get the specific things that we were going to use. And then later we did our experiments for a few weeks and then had a presentation at the end. When I expanded this to a full semester, it was mostly actually at the beginning of the process. We did a more thorough introduction, more thorough reading of the literature and working with developing the hypothesis. We then also added a little bit more time with the experimentation so that if students needed to repeat or change or expand upon their work, they had time for that. That was better. Otherwise the end of the semester is like student regrets. Like if I had more time, this is what I would have done. So it's nice to have a little more time for that. All right. So that's a version of a mini plan. And here is some actual data showing that even a half semester or so cure is beneficial to your students. We did actually do fairly big analysis of this with a large number of students. What we found is, in particular, students in underrepresented groups, just from doing a 6-week cure, reported that they were more likely to conduct research. I know this is a complicated figure, so I just want to show you. You're looking at the dark purple. Dark purple is good. So dark purple is students who are planning to conduct more research. And what we found is that the students who had the experience of doing a short cure, who were from underrepresented groups, had a much higher rate that they planned to do more research. And overall, though, it is more is better. It is true that more is better. A longer duration cure, we got a much higher percent of all the students who were interested in doing more research, as well as other learning gains. They scored higher on a test called the EDAT, an experimental design ability test. They also said they were more supportive of STEM in general, more interested in STEM careers, understood that it was important, and so on. So, but I would say we definitely didn't hurt anyone by starting out small, and it gave us the time, or gave me the time and confidence to expand it, and ideas about how to expand it. And I would also say, think of the experience for your students in the same way. It helps a lot with intro students. They can easily be overwhelmed if you give them a project without adequate chunking up of the project. So I have kind of 2 big projects for the semester that they have to complete relating to the cure. They have to do the proposal, which to them feels like a very big project. And they have to present a poster at the end as a team. So those are my 2 bigger goals. And then everything that I do with the students before that is really helping them to develop the parts that they will put together into those 2 big assignments. So for example, I show them how to use bioinformatics tools, how to use some of the visualization software and Blast and things like that. And everything that they're doing, they're instructed in their little mini weekly assignment that they are supposed to capture an image, write a caption, and all those things that they will eventually then incorporate into their poster or their proposal. So it's ready to go when they are actually trying to put that together. They have most of the raw materials already there. When they're reading the literature, I don't just give them a paper and say, read this. I give them very specific questions. Look in this paper for an answer to this question, or can you summarize what the authors are saying about this topic? And then once they have written that, they have written that, and it is often just fine to move those words onto their poster or to use those words when they're making their proposal. And then during the data collection, I've gotten a little more standardization about like how do we put this in a table? Like how can we organize this data? Or here are the graphs that I think your group should be making. And then again, as they're generating that, I can give feedback if they've made calculation mistakes or something. Hopefully we can catch them at that stage, and then we're not trying to fix that at the same time that they're actually trying to like synthesize it all and make a poster. So whatever you would do, I would just kind of think, where are you going with it? And then make sure that all of your assignments are kind of contributing to the students feeling ready for the bigger work that you're going to ask for them. to do. And then once you're feeling comfortable with that, I would strongly suggest that you collaborate. And we all encourage collaboration in our classes, often just because of logistics. Maybe we have to work in teams because that's the way our materials are, or that's the way our tables are set up or something. But we have found in our work in the MCC that collaboration outside of the classroom is actually extremely beneficial to the students and to the faculty as well. They seem to increase student motivation, they develop more communication skills, and they report that they feel more that they belong in science or they're part of a scientific community. The first collaboration that I would recommend is that you do a faculty to faculty collaboration. So if you have a person at your college that you'd like to collaborate with, that is wonderful. But if you don't, I would bet that in the MCC, you could probably find somebody who's willing to collaborate with you because of the miracle of the internet. These things are a lot easier. And then once you have that faculty partner, then you might be able to think about how to collaborate with your class or their class. And so here's, I'm going to show you a little more detail what I mean by those last two versions of collaboration. So the students collaborating with faculty at another institution, I think this sort of arose a bit, I'm not want to say by accident, but it arose basically because the generosity of some of the people who started the MCC. So people like Ellis or Jessica or Joe Provost, who they've all recruited a lot of us who were beginning the work. For most of us, working with malate dehydrogenase was a completely new thing. For me, doing a lot of the biochemistry was not something I was quite as comfortable with. And for example, with me, Ellis said, "Hey, would you like me to sit with your students while they're thinking through the project?" I said, "Absolutely, that would be wonderful." And then it turned out that my students, I could visually see them working harder and being prouder of their work and being more engaged. And then we realized that this was something that we wanted to do more of, because who doesn't want their students more engaged? So we had, for example, in my class, Ellis visited the class on Zoom or Skype or whatever it was at the time. And he would talk, one-on-one or, with small groups of students, and help them to kind of think through and ask those kind of leading questions like, why do you think that that's true? Or did you think about this? And then did a follow-up visit to hear about what their results were. And then like in my case, at first the materials were also being shared across our labs. And many other people have done sort of a similar arrangement with collaborating with at least a faculty member at another institution. And we had enough data that we could start to quantify that as well and do a comparison. And we found that students who were doing those external, in this figure, it's the EC, that means external collaborator. With external collaboration like that, the students scored higher on that EDAT exam, or test, I guess. They reported more STEM importance and they thought their course was more beneficial. So in general, there was a lot of positivity on the student side and a lot of excitement on the student side, and their communication skills had to be a little more developed. Betsy Martinez-Vaz is at Hamline University, which is close to me. We actually met though in Texas. We were both at a meeting, and then that's how we ended up getting to know each other there. And then our classes started collaborating with each other. I think it was mostly Betsy's idea that we set up our student groups to interact. So she had a certain number of teams working on mutants, and I chose the same mutants to work on that semester. And then we ended up with our student teams being told to talk to one another. And we had a specific little assignment. And when I say assignment, it was, 5 questions. Your group is supposed to get together. They can meet on Zoom or Google Teams or whatever. And then they are supposed to have these sort of guided conversations. So we found that that type of interaction, I also had done with another person's class, I had done a version of this where my student groups were supposed to talk to this other faculty members' student groups when I was sitting there in the room and the other faculty member was in their room. And they didn't talk at all. We like I pushed mine towards the camera and he pushed his towards the camera, and the students just stared at the camera. But when we are not there as faculty members and we have had our students meeting, they feel less self-conscious, I believe. And they actually do talk to one another. They do report that they enjoy the conversation. Some of them, are more reluctant. But it does seem to promote a better interaction without having the faculty members there. But we tried to guide them a little bit with the conversation, especially making sure that they could get over that initial awkwardness. And then they would meet again. So we had them meet early in the process, like kind of around the time they were supposed to be putting together their proposal. And then again, once they had some data to report to each other. And I have a little bit of, this was a little less rigorously assessed, but we did take student surveys. And of the students that were surveyed, they said they felt a sense of belonging. And here's a comment that kind of illustrates that. So the student said, I think it was a very cool aspect and it made it feel like working in a professional field. They did appreciate having a guide, so they knew what to talk about. But again, sort of back to that idea of belonging, I think collaborations with other schools would be a really cool way to become part of the scientific community and get more feedback on our work. And then that having the second meeting, knowing that they were going to meet again together, they said actually made them more motivated to keep records because they thought that somebody would care about what their results were. And they even were curious to see what their partner group's results were. Like the student said, the most positive aspect was being able to see what another group is doing with their mutant MDH strains and seeing if their hypotheses were supported or not. And then they actually, said this was good enough that they would like to do it in another course. And I would like to emphasize that Betsy's students and my students are at different levels and in different majors. So my students were in a Bio 1 class. It was their very first science class. And they were mostly biology majors, whereas Betsy's students were in their third year of a biochemistry program. And that did not prevent good collaboration. Actually, the students said that they enjoyed that, talking to somebody at a different stage or in a different focus area. All right, and now I'm transitioning. I'm kind of handing the virtual baton to Ellis, but I'm happy to take questions if people have them about what I've said so far.
I have one quick one.
Yeah.
So we've noticed, and I'm sure other folks have noticed that there's universities as well, like this really kind of drastic drop in student engagement since the pandemic. And I'm just wondering, since you've been running these for a while now, have you noticed that with the cures, or is that one of the classes where you see that less?
I think I do see that in general, but I think that a cure or kind of anything where you're forcing students to work together as part of their assignment, I think that definitely helps. The students who are in my class with the cure, they have to interact with one another. And I honestly think it's not that they don't want to. I don't know. This is my armchair analysis. I feel like they just haven't had a chance or enough practice to be confident with it. And so I think
Yeah.
we're doing them a favor to give them an opportunity and give them sort of a structure to have
Okay.
those kind of interactions. So that's my hope.
Yeah, no, the social anxiety has definitely gone up as well. So that's
Yeah.
absolutely, yeah. Thanks.
Yeah. Anybody else?
I guess this can wait, but a quick question. Does anybody have anything for general chemistry in specific? Has anybody taught general chemistry cure?
I think Ellis is going to go there.
Okay. Okay.
Yeah.
Okay. Thank you.
So Ellis, if you want, I can just keep running the slides. Is that what you'd like? You can just say, go ahead when you want me to move it.
Right, can you all hear me at least? Okay, I have no clue what happened, and I'm sorry. I apologize, but apparently the Zoom session kept running. Did it?
It did, Ellis. I'm sorry. I didn't even notice. Were you not here?
No, I disappeared.
Oh, I'm sorry. Yeah, it went really
I
great.
suddenly lost complete control and I had to shut down and start up again. But
Oh,
at
I'm
least
sorry.
you
Well, I
guys
said all
were.
kinds of nice things about you, actually, but there is
Don't believe any
curiosity.
of them.
There's a call for more talk about chemistry. So
Well, that's
they'll
sort of
be
what the
glad to hear
second
you.
half of this is going from. So while we're on the slide that Tam's got up at the moment, and I'll just say next, or something when I'm ready for the next slide, Tam, that might be the easiest way to do it. You know, Tam did a fabulous job about talking about a lot of things about biology cures and setting up. And, you know, Tam is the real sort of pioneer for working out how to get a cure started and growing it and whatever. She's done a fantastic job. You know, there are lots of groups that do cures. And all of the groups do vaguely the same sorts of things and have the same sorts of approaches. But it's often, you know, not everybody wants to do malate dehydrogenase cures. That's fine. There's plenty of other great ones out there. Tam already referred to the one that she and Betsy are doing at the moment. You know, most cures are organized more or less the same way and have the same sorts of things. So this is just a list of the cure groups. The one thing I want to mention on this slide is CureNet, because CureNet is a phenomenal organization that's really compiled lots of information about cures that exist around the country. But more importantly, I think has developed a great way of approaching starting a cure, from building a cure and guidelines, things like that. So, you know, yes, jump in and do a malate dehydrogenase cure or whatever you choose. But my strongest piece of advice is to go to CureNet and go through the process of getting your cure that you're developing up on the CureNet page. Because by going through that process, your cure will get a lot better. And I say that as somebody that's been through that process about 3 times in the last 5 years. And each time I go through the process, I get better at putting my cure together. So, you know, my strongest advice is to do that. In terms of sort of developing ideas for a cure, we've put together a website that's called Our Cures. Uses for all of the different sorts of cures. And there's some guidelines on that for developing your cure. Okay, so with that, I'm ready for the next slide, Tam. So you sort of have seen this because Tam's version was more or less the same as this if you look, though you'll notice that there are so-called 9 elements of research laid out in this particular one. So if we start at the bottom and work our way up, you'll find it starts with relevance, which, you know, was on Tam's list, explore scientific background on Tam's list, hypothesis development on Tam's list, present a proposal on Tam's list. And these are things that show up on most of the lists that are out there. Do experiments, obviously. It's a lab course, so you can do experiments. One thing, especially in introductory courses, especially when you're trying to convince a department or a program to let you start things, costs become a consideration. And one of the things we've done And there's some links through some of the links that are in this PowerPoint. This PowerPoint will be up on the website after the fact. Is there are lots of computational approaches. Pam mentioned using Primal, but there are lots and lots of other cool computational approaches that are free and don't need specialized equipment and don't need, expensive reagents and things like that. And, a lot of us in the protein-oriented world were driven to them by COVID. Is actually, I think, one of the good things that came out of COVID is that we learned how to adapt and use free computational resources to do research with. And so as we get into the one I'm going to talk about in detail a bit for freshman chemistry, you'll see that, we've melded together computational resources and wet lab resources. And, it's a way of keeping costs down. It's also a way of letting students have more time out of class to follow up on things and do research, because they can sit there and submit computational jobs from the local Starbucks or wherever. So it's a way of, and all the things that Tam's talked about, I'm going to talk about as well, about how to structure your cure, apply to computational resources as well as, the wet lab type resources. So Tam had reproducibility on her list. It was part of design and execute experiments, but that iteration reproducibility is an important part of science. We all know that as scientists. And one of the things that I do in all of the cures that I teach is about midway through the semester, as they've gotten comfortable with doing things and started to get data and starting to think about presenting the data and analyzing, drawing conclusions, is challenge them to reproduce one of the experiments that they've done that they think is really critical to their project. And I do that for two reasons. One is, earlier on in the semester, and I'm sure this is something that we all do anyway, we talk about the importance of accurately recording what you've done. That seems to be a highlight in all of the introductory science labs sort of requirements, is that students learn how to do this. And it's really quite illustrative of the need to do that if you suddenly ask a student to reproduce an experiment they did 3 or 4 weeks before. And they realize maybe my recording of the detail wasn't quite as good as it needs to be. And so it sort of stresses that, which is a critical element of science. And so, most of those, the added on one is peer review. And I found this is really, really helpful to the students. So, Tam talked about doing mini assignments and I love your idea about the proposal presentation, having them pre-record it. I think that's a great, I'm going to steal that one from you, Tam. But, whenever there's any sort of presentation or assignment, I get the students themselves to peer review one another. And I have a rubric and they have to, these are things I liked. These are things that didn't come across clearly or whatever. And I challenge them to identify something from other people's presentations that they wish they'd thought of and done. That whole peer review aspect of science, we live with it every day. Basically, if you write manuscripts, you live with peer review. If you write grants, you live with peer review. And it's an important part of science. And so that's the added part that's not on most people's lists, is that peer review. But I found it's a great way to engage students in learning from one another and being actively involved during presentations. You know, otherwise there's a tendency, if they've not got something that they've been assigned to do while somebody else is presenting, they're either jiggling their own presentation to get it ready, or they're on Facebook or whatever. And this way they stay engaged. Okay, so next slide, please, Tam. So this just illustrates, you know, the verbiage that's in our general first year chemistry labs, because, you know, I've taught cures in everything from upper level classes to first year classes, and I suspect you all may be in a similar situation to what I'm in here in San Diego, and that is there are 10 sections of GChem lab in the first semester, one of which I teach. And I teach it the regular way that everybody else teaches it in the first semester. But in the second semester, I've converted my section, and again, there are multiple sections. I converted my section to a cure lab. And so they do a lot of the standard techniques in the first semester. Second semester, I started doing a cure lab, and now several other faculty have started doing a cure lab. We've got an environmental chemist that's doing a cure lab in second semester GChem. We've got a material science faculty person that's doing a second semester GChem lab. And, you know, we all have to have the same basic components in there and fit them in. So at the bottom of this slide, you know, the sort of, upon completion of this course, you should be able to, okay, there's a list that's prescribed, and whatever you're teaching, if you're not teaching the pre-prepared cookbook labs, you have to go with incorporating these things into them. And it's, you know, it's fairly easy to do that. They're fairly, I think you see, keep a basic laboratory notebook is on that list. But, you know, you can generate a cure on pretty much any topic that you like, but, you know, keep in mind whatever the department, especially if you're the lone wolf in a multi-section course, or a small pack of wolves in a multi-section course. It's still basically possible to get all the departmentally required learning outcomes. So next slide, please. And these are the learning outcomes for the second semester, GChem at USD. I'm just going to talk through these in a little bit more detail to sort of show how I incorporate bits and pieces of this. Okay, so design a simple experiment that can answer a given chemical question is one of the requirements. You know, that one's in chemistry, at least, that one's fairly straightforward. Certainly, you know, the comparable statements usually in intro bio courses as well, but, you know, that one's pretty easy with a cure. Qualitatively analyze a given chemical or physical process is one of our requirements. You know, observe a chemical and or the changes that take place in a chemical reaction. Perform a flame test or a precipitation test. Test for acidity, basicity, identify unknown from qualitative tests. So, you know, the cure that I teach actually hits pretty much all of those. We try not to set fire to too many things, but, you know, there's ways you can incorporate a simple flame test into something fairly easy, and we hit all of those points. And then the quantitative aspects, which I think are really important to emphasize in intro chemistry courses and intro biology courses. You know, generate and interpret a standard curve, interpret titration results, calculate percent yields for a synthesis, apply kinetic, weak acid-base equilibria, those sorts of things. You know, and I try to hit all of those in my GChem cure. So next, let's get into some detail. So the course I teach in the GChem sequence is called An Introduction to Chemical Thinking Through the Lens of Anti-Malarial Drug Design. And we focused on malaria now for a couple of years. I'm tempted to change the parasites. But, you know, there's lots of good parasites out there, lots of fun parasites. You know, we might do it with brain-eating amoeba soon and things like that. But the full description of this class is on the CureNet, and there's the link to the CureNet. And as I just said, you know, the students they have a choice of doing a regular second semester cookbook lab or a cure lab. And what we found since we've started doing, you know, 2 or 3 of the sections do cure labs, the cure labs fill up instantly. And then, so there's sort of pressure for more people to do cure labs. Okay, so next. You know, this is out of my syllabus. It's all laid out in the syllabus for them. So next. Just like Tam talked about with her biology, we try to do this or have options to do this as both a modular cure or a full semester cure. And sort of like Tam, a lot of us started by introducing it as a modular cure and growing it to a full semester cure. And the purpose of this is to just give you, just like Tam did, an idea of what sort of activities we do and which of those cure elements we hit, so that the students understand they're seeing all of the cure elements of research as part and parcel. And so, you know, starting hypothesis development, and we published some things on Course Source about hypothesis development, and there's some more stuff coming about hypothesis development. ACS has just finished a book on cures in the life sciences that Betsy and Tam and I and Kevin and some other people that we've mentioned have been involved with. That's coming out in late January or the very first week of February. And it's got lots and lots of examples and lots of resources, many of which are on the website that I pointed to earlier, but, you know, it's another resource. Okay, so if we can go to the next slide. So, you know, after there's peer review again, then we do experiments, whatever, and usually then there's a gap, just like, you know, Tam talked about in biology, cures. You know, it's easy to fulfill departmental requirements if they don't fit in your cure in labs in there. And then, you know, it's final presentations and whatever. So you can do it in a modular cure with chemistry, just as you can with biology, or you can do a full-blown semester cure, which on the next slide is a starter. And this one's got lots and lots of stuff on it. So I'm not going to try and step you all the way through it, because you have access to this PowerPoint anyway, and you can read all the things. But just like Tam pointed out, chunking it into doable pieces is a really great idea. And planning for some flexible times, because things never go as smoothly as you think they're going to go. And so, you know, don't try to overschedule things. leave time for some redundancy. What I call snippets of the little written assignments that sort of, TAM uses the same sort of thing to get students to think about and write and present data in a snippet or whatever. But this gives you sort of the layout. Because it's about drug design, we do a lot of stuff about structure of molecules and how molecules interact with one another. So there's a lot of stuff about non-covalent interactions that builds off of stuff they've seen in the lecture sections. There's lots of stuff about the shape of molecules and those sorts of things. There's protein, but we do a lot of stuff where we mesh computational approaches with wet lab approaches, so they can screen inhibitors by measuring the rate of the reaction of the enzyme catalyzed reaction, and then doing it in the presence of varied concentrations of different inhibitors, things like that. And they can match wet lab with computational. They do spectroscopy because they have to be able to determine, their reaction products spectroscopically and the amount of protein they're using. So all of those things, like a standard curve and spectroscopy and rate laws and all of those things come into it. I think on the next slide is the latter part of the course. And this is where we got creative to fulfill one of the requirements. So one of the requirements was that they see a new technique that, that's not just spectroscopy or an application of it, whatever, and that they do titration. So right at the start of the semester, we talk about properties of drug-like molecules and what a drug-like molecule has to do. And, there's something called Lipinski's rules for drugs, one of which is about, what sort of interactions they make. But one of them is about their solubility and their ability to go through a membrane. And that actually led to a cool incorporation or extension of a titration experiment and a phase separation experiment. So they got to see titration and a new technique, phase separation. And when I started doing that, you'll go, oh, that's great. They'll know something that we're going to have to teach them again in organic. But, she was delighted that I was putting a phase separation. So they do an octanol water phase separation of the compound, and they have to work out, whether or not the drug molecule fulfills Lipinski's rules and would go through a membrane, and that they're allowed to sort of we have a whole bunch of things available, but they can try and then design something that they think would fulfill Lipinski's rules better computationally. And we're building towards sort of getting a follow-up cure in organic, where they actually then try and synthesize it and then would come back in biochemistry later and test the synthesized compounds as opposed to just screening. So we go through high throughput screening, we go through structure activity relationships and all of those sorts of things. So that must have been the last slide, I guess. So, or have I lost you all again? No? Can you still hear me? Okay, good. I was worried. I think that's pretty much the, oh, well, yes.
Yeah, sorry, that one was me. I lost
okay.
my connection.
I thought, oh no, I've got again. So this is the build, continuation of what Tam was talking about collaborations. And these are two papers that we've published, one in Course Source and one in CBE Life Sciences, where you can see the second one has got some great guidelines for how to organize groups and things like that. This one reports the pedagogical research activities. But, as Tam emphasized, it can be faculty student, it can be student student, they can be from different institutions, they can be from different classes in the same institution. And all the evidence we have is it's beneficial for the students and it's fun for the faculty, and it helps you develop, and I think we've all learned more about how to structure our cures by collaborating in these sorts of ways. Is that the last slide? That is the last.
Yes, that is the last one. Yeah, let me stop
So
the sharing.
one slide that I usually show at the end, I guess I didn't put it in this time, but I should have. But it's a slide about high impact educational practices. And it says that high impact educational practices usually involve learning at the edge of chaos. And I overlay that with your job when you're teaching a cure is not to eliminate the chaos, but to control the chaos. And, work on the principle that it's going to be chaotic at times. So, the other thing is when you first start with a very structured sort of research project. The drug design one is a fairly structured research project. As you get more and more used to it, it's sort of fun to give the students more control over where the project is going to go. And so this semester, in my upper level biochemistry cure, I said, the only guidance I'm going to give you about the project is that it has to involve malate dehydrogenase in some way, shape, or form. Work out what your project is going to be. And each student then started thinking about the relevance, because we always start at relevance. And so somebody wanted to do something about Alzheimer's, somebody wanted to do something about something else, somebody wanted to do it. Fine, develop your project around that. And it's been very chaotic because they've all, instead of them all focusing on the same scientific question, they're all focusing on different scientific questions. But I got to tell you, it's been a lot of fun. And I think they've enjoyed having that control. So I'm going to slowly start sort of back engineering this into my first year cure. Not quite with as much freedom, but at least with a bit more freedom to it's when the student is invested in the relevance of the project, they're going to work harder, they're going to have more fun, and they're going to get more out of it. So I think with that, I'm done with what I wanted to say. And so questions, comments, thoughts. I think the most important thing is, connect with the folks that are doing the sorts of cures that you're interested in. And it doesn't have to be MCC. We've got lots of great people doing lots of cool things with malate dehydrogenase. But, adapt to a different protein. Join one of the other groups. But cures are fun and they're important.
Alex, I have a quick question on your anti-malarial drug design course. So students who get into that course, what kind of chemistry background they have before getting into that one?
They have general chemistry 1.
Okay.
They learn what a molecule is and what a reaction is, and they sort of know how to balance an equation.
Wow. So
And
no
they're
biochemistry background,
they don't have any biochemistry, often no biology.
no kinetic, no thermodynamic,
No,
nothing.
no, they get that while they're taking the course, because they're taking GChem 2 while they're taking the course. And so I try to mesh with topics that I know are coming up in the lecture section. So, you know, they get the kinetics, the thermodynamics. And,
Oh, I see. So while taking this, they're taking general
right.
chemistry too. I see.
Yes, yes.
Got it.
They're taking the lecture section, and this is the lab components of that lecture section.
Thank you.
And, you know, it's great if you can to pair with a biology faculty person. You know, it was taking a GChem cure lab that somehow paired with a biology cure lab be really powerful.
So for your biochem class where you did like the free for all, they could do anything. How many students did you have for that?
8.
8. Okay. I almost sometimes have 50, so I was just
I
curious.
have 20 in the drug design one.
Okay.
And I've done a cure with as many as 30 some biology students in the past.
Okay, so about 30 is the biggest class you've done?
Yeah, and it's usually restricted by the space available.
Sure. Okay. Thanks.
Yeah, we're not allowed more than 20 in the GChem lab.
That's true. Yeah.
I don't know if this is too much to ask, but are either of you are you willing to share more materials from your courses? Because I am teaching General Chemistry 2 lab for the first time this spring, and typically it is run more like a cure. And in the past, it's been taught by an analytical chemist, and I'm a biochemist. So I'm looking to move like into this realm, and I want to do it. I just feel like I don't really know like how to start with 24 students in Gen Chem 2. So is that something you to do? I don't know. I know it's like a lot of work that you've put into it, so I don't want to ask too much, but I didn't know if the resources.
No, you're not asking too much. And in fact, that's what the community is all about. I'm happy to share any of the materials that I use. In fact, a lot of them are on my website already. But, you know, I meet with several people that are teaching, you know, cures on a regular basis to go through materials. Sahaja at St. Martin's, as I see in the picture. You know, we talk about this sort of stuff all the time. I'm happy to share. So
yeah, me too. Mine is a little less relevant, but I have things like you know, poster rubrics and how to do a proposal, those kind of things. I'm sure you could adapt to whatever.
Kelsey, if you like, we can set up a weekly meeting as you're going through it, or when you're developing it, whatever. That's worked well with other people.
Awesome, thanks.
Sahaja?
Yes, yeah. So Tam talked about faculty to faculty collaboration. I can speak to, you know, how much Alice has mentored me through the last 2 semesters. And Kelsey, I'll be teaching a Gen Chem, and I'm interested in doing a cure. So when you set up your meeting with Alice, I would like to be part of that, and maybe our students could collaborate. I'll be teaching 3 sections, but 24 students in all. It might be a good way to, you know, get the students together and for us to collaborate with
Alice. Well, we can have a 3-way collaboration. That'd be fabulous.
Excellent.
Other questions? Yes, Lynn.
Do you do this in teams? The student works in teams, and what size teams would they be?
So I do it with pairs of students.
Okay.
I
try to avoid the bystander syndrome.
Yeah, I have 4s just because I have to. I have 24 and we have 6 tables, so like it's weird to do it any other way. But even then, I have also it's a community college and first year class, and so we also have a large number of students who don't go all the way through the semester. They have life circumstances that prevent that. So I also actually duplicate everything within the class. And sometimes there's multiple reasons why I have settled on the number of mutants that I use, but I always use 3 mutants every semester. And one reason, which will sound stupid, but there are 4 holes in my big bottle centrifuge, and I can do the 3. I'm purifying. I can do 3 mutants and a wild type all at once. But also with the 6 tables, then if some like horrible collapse happens in a team, there's another team that is doing the same work, so they don't have to start all the way over again if something like that occurs, or if one group has a bad day and they don't get data. Sometimes they're sharing between the groups. So there are definitely bystanders and hangers on. It'd be nicer to have smaller groups, but there are some good things about a bigger group too. So
Thank you.
Lindsay.
I have 2 questions. So Montana and I are going to be working together. I'm hoping to produce protein for Montana's Gen Chem 2 class, but since they're actually held at the same time, at least I think our labs are held at the same time, I'd love to try and collaborate more between classes. What kind of, I guess, things should I keep in mind as I'm talking for a junior senior biochem class and a freshman Gen Chem class that might facilitate better communication between them and not be too much for one and too not rigorous enough for another?
I would incorporate specific questions that encourage them to kind of mentor one another. I think and you might think that's only benefiting the first year students, but I think students who have made it a little ways through a program, I think they feel so like such a sense of pride to be able to say, like, I can give you some advice. I know a thing and I wish I had known it before, and I'm going to tell it to you. So I think having part of your assignment be just a little bit of sort of like career coaching or career discussion is a good idea, in addition to the science part. But if you can like emphasize the angle, I think it can help make them realize that they might have a perspective that's different than the others. Like I said to so I also had my genetics students collaborate with Betsy. So I've had like there's been 3 different classes collaborating. And I always told my genetics students, I said, oh, you know this a little bit better from a genetic standpoint, and they know it a little bit better from a biochemistry standpoint. And that's a lot of times why we are collaborating, as real scientists. That's what we're trying to do. We want to get expertise or perspective. And so maybe emphasize that they have slightly different perspectives, and that they could try to, use that in their conversation.
Yeah, I endorse what Tam just said, 100%. Great comment, Tam.
Thank you. And I have one question about developing a Gen Bio cure. How well do they understand all the different concepts? Because I just went through a different type of molecular techniques lab set, and I see a lot of questions coming in. So I don't want to overwhelm them, but I also want to prep them for cell and molecular.
I would say, so when I was first doing this, I was doing it with my Gen Bio class, which is probably similar to yours. Mine had no prereqs at all. So they might have been in chemistry at the same time, and they might not have. And other people were doing a similar cure in much higher level class. So it looked like we were doing the same thing, but what our students got out of it was definitely different. I think as long as you have an appropriate, like, these are the things that I would be happy if they learned. And if you can satisfy yourself at the end, they didn't understand everything, but like mine, one of the things I know they take home is they understand that a changing of an amino acid in a protein is important because, and then they can kind of start to explain that and sort of that emphasis on like what an amino acid even is, and that amino acids are different from one another, and primary structure influences tertiary structure. Those sorts of things that come through really strong. Some other things I de-emphasized some of the calculations because I don't have a math prereq. So I show it to them, but I don't make them do it in that sense. I have it set up in a spreadsheet. As I've gone through, I've sort of decided what is and isn't something that I'm willing to spend a long time explaining. So I think it's worth like thinking it through a little bit, but then you probably will develop your ideas once you've tried it. There's some things that you don't realize that are like layered into your project or your explanation until you get there and you're like, oh gosh, now I see why they don't get that, because you know, I know this thing and I don't have a quick way to explain that thing. But I think, yeah, I think it's totally okay to do a similar project to another class, but get different things out of it just because your students are ready for a different level. That's okay. As long as you feel that you are getting them to the level that they need to at the end of Gen Bio, then it's okay to do a more complicated project and have the students get a lot of it. I mean, and also probably you have the same kind of group that I do. There's some students that are extremely ready and excited and can carry it very far. And it's nice for them to know that there's more, you know, so to sometimes say like, okay, I'm going to tell you a little bit more, like, let's talk about this and we can go a little bit beyond and not necessarily think that everyone in your class has to go to the same place.
Thank you. That's really helpful.
Yeah, and I would just add to that, when I was in Richmond, I taught a first semester intro bio cure, and I had control of both the lecture and the lab, which was nice because, you know, while I was teaching them about DNA replication and DNA structure and those sorts of things, we were actually doing those things in the lab and making mutants. And that brought up, you know, all the sort of things you want introductory students to think about. And so it worked great. It was a lot of fun.
Thank you. That's really helpful as well.
Any other questions? Then we'll probably let you all get on because it's Friday and it's getting later on the East Coast. But keep in touch. Both Tam and I are happy to answer questions offline. You know, email us, use us. That's part of what having a community is all about. You know, we both benefited from it and we're happy to help in any which way we can. So keep in touch with us and let's have some fun with cures. Okay, guys, have a great week.
Thank you.
Good
Thank you very
seeing you.
much.
Great conversation. Good
Thank you.
questions. Hi, Sanju.
Hi, so tell me how to say your name correctly. Is this Salija?
Sailaja, yeah.
Sailaja. Okay,
Yes.
my email, I can tell it to you really quick.
Yes.
It's T
T.
Mans, just T for Tam and then Mans, no
Okay.
periods, and then at nhcc.edu.
Okay, got it.
Yeah, and send me an email for sure, and that way I'll make sure to get you anything that is helpful.
Okay.
Yeah,
Thank you very much. Thank you.
nice to talk to you.
Nice to talk.